Thank you. Okay, so I hope that you have already have a look at it, and then you already know what we are going to discuss today. And I am expecting that you are having some questions on that, so that we can discuss in more, and you can have some better understanding of what we are talking actually, on what page are we now. Rather than just listening to me. That's why we published, or I made this, I mean, we make this lecture slides available to you prior to the class, so that I hope that you will go through and then you will ask more questions. You will have more questions so that you will ask. All right. So without further ado, I go to that lecture slide where we started. Where we stopped last time. Where is it? We stopped at the electronic configuration, right? So I am hoping that you know what is the electronic configuration and how to do or how to show the electronic configuration for an atom on the periodic table. And now many times we are talking about the periodic table. So you might also ask, or you might have some question that what is periodic table and why we are talking so much about. And I mean, we all know what is periodic table, but what information does it give to us, right? The periodic table. Looking at it, what can we get? Or if we want to look something specific, where to look at? So all those things we will be discussing in short. But just a reflection from yesterday class, that how do we do the electronic configuration for an atom? How do we fill up the orbitals of electron, the configuration? This is the way that we fill up that in every subatom, sub-level, suborbital, there will be 2 electrons, maximum 2 electrons possible, according to Pauli's exclusion principle, that 2 electrons are possible to stay, and then both of the electrons should be opposite spin, right? If one is rotating clockwise, another should be counterclockwise. But just to note here that if it is a clockwise, it is not all the time clockwise, because there is a spin clock and anti-clock, and then the other is counterpart should follow and go the opposite spin of that one. Okay, so just for information, but this is the way that we show that one will be one side spin, the another one should be other way. Okay, let me go to the full screen. So now I'm the full screen. I cannot see your chat box. If you have any question, and yeah, I hope that you have question, please unmute yourself and talk. It's much pleasant that way. Okay, so now this is oxygen, and we know this is the period. This is how the electron configuration looks like for oxygen, but on an energy level, how do we see what energy or how the energy is distributed, and which of the electrons has more energy or less energy? So on this energy level, orbital filling sequence, with the increasing energy, we can fill up this one as well. Okay. So for sodium, we have seen it yesterday. For sodium, there is only 1 electron, and that is a valence shell electron, that is called, because this electron is responsible for making the bonds for sodium. All right. So this is our periodic table. And then there are the blocks, right? The periodic table, the whole periodic table has been divided into few blocks, precisely 3 blocks. Okay, so this one is 1 block, and we call it S block. This middle one, that is lower in a bit height, that is called D block, and then another one here on the other side, on the extreme right side, we call it P block. So what does this S, D, and P means? It means that at the end, the last orbital for all these elements here are S orbital. Okay, so this is called S. The last orbital or valence shell orbital for these elements here are D. The orbitals are D. The electrons are at the D orbital. It can be 3D, it can be 4D, it can be 5D, but it will be in D orbital. The last electron should have, or this element should have the D orbitals themselves. And these elements here, they should have a P orbital at the end, or all of them. The common thing is P orbital. Here, it doesn't matter. I mean, it is not, I'm not saying that all of them have the same P. Someone, they will have 2P, there are 3P, 4P, 5P, like this. It will go on and on. So this way, the periodic table has been divided into 3 main blocks, S, D, and P. Later on, we will see that yeah, there are some division in between the S block, whether we call alkali and alkali earth metal. This is the metal, and there is a pure metal. This is metalloids, and then there is a non-metal gas, noble gas, and so many things. I mean, many ways we will divide it. Okay, so there is another one here. This falls in the D block, but this is an lanthanide and actinide series, but we will not be discussing in it. Sorry, this will be in 4A, I mean F block, okay, F block. So that will be in lanthanide and actinide, but we will not be discussing it. Okay, so this is, for here, it will be 1S, because these two, oh, another thing I should mention that these are the period. Okay, these are the okay. This is 1, 2, 3, here 4, 5, 6, 7, 8, 9, 10 until 11, 18. Sorry, until 18. They are the period, and you can say that the periodic table came up in this way. And they are the groups, like 1, 2, I better write it. Okay, so this is 1, 2, 3, 4, 5, 6, 7, and this way it is a group. They are grouped up in this way. Okay. All right. Or okay, so another thing, it should be group here and period there. All right. So this is for group 1. It should be group. Okay. So this is group 1. It was in a previous slide. It says it's group, but it's actually period. So period 1, period 2, period 3, period 4, and these are the groups. Okay, group 1. There is a mistake here. I will correct it later. Okay, so this is group 1. In group 1, there is hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So all of them has s orbital at the end. The last orbital is they have available s orbital at the end. The electron can stay or can be found at the s at the last one. So 1s, 2s, 3s, 4s, 5s, 6s, it goes down in this way. For these metals or a D block, okay, we see that here the scandium, titanium, then chromium, magnesium, they all have 3D, and then the next period they have 4D, 5D, 6D in this way. So this is what we were talking about, that this is, they have been divided into S block, this is D block, and this is P block, right? So all of them have P, available P orbital at the end of their, the most outer shell orbital is the P, here D, and here is S. All right, so now since we are familiar to the periodic table, and then we can see what to look at and how can we find what block of element on it. I will go in detail in few minutes, next few slides for this periodic table. But before that, there is an exercise. It says that write the ground state electron configuration for sulfur. All right. Point out how its electronic configuration is related to sulfur's position in periodic table. If we see sulfur, all right, we will see that it has 32 electrons, right? And then 16, sorry, it has 16 electron because there's 16 protons, so it has 16 electron, and its atomic weight is 32 actually. So we can write the sulfur electronic configuration in this form: 1s2, 2s2, because 1s2 means there can be maximum, and according to the Hund's rule that we have seen, above principle, that it will start filling from the lower energy state, right? So this is 1s, one is opposite spin. There can be maximum two electron can stay here. So same goes for 2s. This is 1s. This is 2s orbital. And also there can be maximum of 2 electrons here. And then there are 2p. And there are 2p means 2px, 2py, and 2pz. So 2px, there can be maximum of 2 electrons, means this one. 2py, there can be a maximum of 2 electrons as well. And 2pz, there are maximum of 2. So, and this is why we write it 1s2, 2s2. This 2 is the number of electrons, that maximum number of electrons are staying in that orbital. Here as well, this 2 means there are the maximum number of electrons staying. And 2p6, because there are 2, 4, and 6 electrons are here. So altogether, without showing all the sub levels of the, sorry, not x, not x, but we put just 6, so that we show that the maximum electrons are staying in this 2p. Now we see that altogether 2 plus 2 plus 6 is 10, but I have another 6 electron, so that 6 electron will move to the next orbital, and next orbital starts with 3s, because 2s is taken, so it will be 3s, and there can be maximum of 2 electrons, right? And then there are 3p as well, and all p has 3 subsection or subatoms, subatomic level, and that will be 3px as well, 3px, 3py, and 3pz, that way, okay? So maximum of 2 electrons they can have. one can have maximum of 2 electrons. So I have 10 already, and then in that 3s there are 2, so plus 2, that means 12, and then I have balance of another 4, so that it will be 16 for sulfur. So that these 4 electrons, how do we distribute these 4 electrons in that P is, as we say, that it will fill up all first 1, 1, 1, and then the rest will fill up here. So that you cannot just put here 2 and leave this empty. You cannot do that, okay? If you do this, it will be wrong. You cannot do this. So what we have to do is they will fill up 1, 1, 1 first, and then the if there is any leftover or any extra, that will be filled up from the beginning again. If there was 17, it will fill up here as well. So this is how it will go. Okay, so now we see that there are another 4 from 3px, and it all together is making 16 of electrons. Okay, so it is 16, and now what is the last orbital it is having that electrons are available is p, right? Is p. So since it is p, it will be in the p block, isn't it? It will be in the p block in the element periodic table, p block. Okay, so it is on the periodic table in the p block, and then it is 3p or 3s and 3p. So here is 3p, so that it will be here, it is positioned in this place. Another is asking that okay, no, all right. So this is what it was asked, that where is sulfur mentioned, where is sulfur? So sulfur is actually on the 16th because it is having the 16th electron at this in this period. Okay, now since we see already that the periodic tables are here, right? Periodic tables are here, so we know that what we can expect and what we can look into if we have any elements given to us, or we are looking for some specific element. So another way, okay, I'll go there later. So now we see that due to this division or dividing them up into the S, P, and D block, we can find how or where to look these for the elements, and where can we exactly find it if we know the electronic configuration, or if we do not know the electronic configuration, still we can have some idea that where it will be based on their property, whether it's a metal, it's a gas, or it's a non-metal, or yeah. So based on that, we can also have an expectation or a rough idea of where we can look into that. Okay. So write the ground state electron configuration for palladium, and use the electronic configuration to predict whether palladium is paramagnetic or diamagnetic. Another thing that I'm not sure whether you have noticed, the ground state electron configuration, we can say. So ground state electron configuration means that when the electrons are stable and the element is stable, the electrons are not excited. When the electrons are excited, they will jump to the next orbital or next level, and that is the different case. It depends on how the energy it absorbs, or the the energy is provided to it. So it will be different from this ground state. In this ground state means when the electronic configuration is like this, it is not excited, or it is stable. It is stable, or what we can find the sulfur in this way, like normally we can find. So that is the ground state level. It's not excited. It's normal actually. That's what what was given or shown. Okay, and for the palladium, is the ground state electronic configuration for palladium is okay. Let me check what is the palladium number of electrons it has. Palladium's electron is 46. Okay, so it has a 46 electrons, and then for 46 electrons, how 1s2, 2s2, 2p6 in this way we will fill it up, and at the end we see that it goes up to this 4d and 10. So 4d 10, and then here, okay, this thing I did not mention, I forgot to mention. Okay, this is neon, right? This is neon configuration. So if we look in the periodic table once again, if we look at the periodic table, this is the noble gas, right? I think you know that this is noble gas. Okay, so this noble gas noble gas are those who are very stable. They do not have any deficiency of electron, or they do not have excess of electron. They have just enough electrons, so that they are very stable, and that is why they are noble in that sense. Maybe it's called because they do not want to react, or they do not want to go into the reaction or interaction with others. But there are some difference as we go down the group. We will see that they actually do some reaction. Later on, we'll see it. But usually they are very stable, like helium, neon, argon, krypton. They usually do not go for a reaction. Whatever is the condition you provide, usually they will not go into that reaction because they are very stable. And all of these atoms or elements that we see on the periodic table in that same period, right? The same period, like for this period, potassium, calcium, scandium, titanium, chromium, what is B? Vanadium, all of them, gallium, all of them, they want to attain this chromium or argon structure. The first of few of them will try, probably it will be easier for them to attain the, or want to be argon structure, electronic structure. Some of them would try to attain this krypton structure, because everyone wants to go there, because after that they do not have to be active. They can just relax, and then they don't have to care about where to go, take an electron, give the electron, like that. So everyone wants to attain this noble gas structure, electronic configuration. So that is why it is shown in this way, that when it is 1s2, 2s2, 2p6, this is actually neon gas structure, 1s2, 2s2, 2p6, right? So this is neon structure. 2p6. So this is neon structure, and you see that they have their octet filled up. They do not need or need to take or give any electron. They are very stable. They have no other space for electron to absorb or take. So they do not need to give to others as well. So this is a neon gas, neon structure. And this part, 1s2, 2s2, 2p6, so this part is represented in this way, that it is a neon structure. They have attained a neon structure. On top of that, there are 3s, 2 electron, okay, in 3s, and 3p, 6, 4 electrons on top of that. So that is how it is represented by this representation. It means that it has neon structure first, so that we don't have to write this 1s, 2s, 2p, and then on top of that neon structure, it has 3s2 and 3p4 structure electrons. For palladium, it has 46 electrons, and then it is, if we look until here, 3d10, right? Sorry, 4p6, it will be krypton structure. Until here, it filled up, or it fulfilled the krypton structure. On top of that krypton structure, there are sorry, here it is. Okay, on top of this, there are 10 electrons excess, which is in D, 4D structure. And it says that whether it is a paramagnetic or diamagnetic. Now, paramagnetic is the characteristic of an element, that it will be attracted by the external magnetic force or magnetic field. External magnetic field, it will be attracted. Paramagnetic, diamagnetic, it will be repelled. All right. If it is diamagnetic, then it will be repelled by external magnetic field, and if it is a paramagnetic, it will be attracted by external magnetic field. So when there is an unpaired electron, all right, unpaired electron at the outer shell, the outermost shell, then it is a paramagnetic. It is unpaired if it is an unpaired. And diamagnetic if it is a paired electron in the outermost shell, then it will be diamagnetic. So here is 4d10, although D can have more than 10 actually. So it is, no, D can have maximum of 10 electrons. So because D has 5 suborbital, so that it can have maximum of 10, and it is filled up maximum of 10. So that it has 10, that means even number, and it is what I said just now, this is unpaired. These all are paired, that means 5 paired orbitals are there. So that is why it will be diamagnetic. It is not a paramagnetic. All right. So it has D and 4D10. So there are 10, and all of them are paired, so that they are palladium is diamagnetic for this case, and it will be repelled from external magnetic field. Okay, so now we move on to these molecules and ions. All right. Okay, I forgot to turn off my camera. Oh, Jonathan, actually you said 46, but I did not see it. Okay. Now I'm going to the full screen mode again. So if you have any question or anything, keep in. Please unmute yourself and then talk. Okay. Molecules and ions. The percent composition We will learn from here the percent composition, empirical and molecular formula, formation of ion and molecule, and chemical formula and nomenclature of binary compound. All these things we will learn in few slides. And for this percent composition, empirical formula and molecular formula, when there is an empirical formula and molecular formula, these two terms, that means there are two ways to express or show the result, not result, that the structure of a molecule, right? And percent composition, we already have seen the percent composition, like how to find the percentage of an atom in a molecule, right? We have seen that C2, sorry, H6O, right? From there, we saw that how many percent of carbon is there, how many percent of hydrogen is there, how many percent of oxygen is there. We have already seen it in the previous lecture. So now in this lecture, in this section, we'll see what this percent composition actually means for how can it help us to understand the empirical formula and molecular formula for a chemical or a compound. Empirical formula is the ratio, the simplest ratio of atoms in a compound, just like this C2, we have seen C2, H6 and O. It not necessarily that it has to be CH3, CH2O, OH, right? It can be any other compound. It can be any other compound, but there are in the molecule, now we see that there are 2 carbon in that molecule, 6 hydrogen atoms and 1 oxygen atom there in the molecule. So this is what we see in the empirical formula. But if we know, and the molecular formula is very detailed, so that we know this is the molecule, like this is a it's a methanol, or it's an ethanol, or it's an alcohol, or it's a sulfuric acid. Exactly, we know what is the identity of that chemical or that molecule. So CH3, CH2, OH. So this is a molecular formula because it is very detailed. It cannot be any other compound other than ethanol. This is ethanol, right? Ethanol sometimes is written OETOH in short to save time and effort. So this is ethanol. This is also ethanol, but it can be anything else. It can be anything else. CH3, then CH2OH. So something like that. It can be something like, oh, is the something, right? So actually it can be anything else than ethanol. It can be anything else than ethanol. Nothing comes to my mind right now, but other compounds or other elements can be formed from these 2 carbon, 6 hydrogen and 1 oxygen. So from this empirical formula, we cannot for sure, certainly, with certainty, we cannot say that this is ethanol. But with this molecular formula, there can be nothing else other than ethanol or specific element or a specific compound. All right. So that for this empirical formula, we need the percent composition of each element, and then we will find empirical formula of the compound can be determined from that. For this one, molecular formula, we have to know the empirical formula first, and then the molecular mass of that compound, and from that knowledge only we can find this molecular formula for one compound. Here there is an analytical problem here, that the ethanol was burnt in presence of oxygen. All right. In presence of oxygen, ethanol was burnt, and then in presence of oxygen means oxygen is channeled into this funnel, and ethanol was placed here, and there is a heat given, so that ethanol was burnt, and from that ethanol, water. We already know that from if we burn ethanol, water and carbon dioxide will be produced, right? So water first, of course, carbon dioxide and water both are producing here, yeah? Don't become confused that water and carbon dioxide both are produced here. So this both produced gas is water vapor, all right? Water vapor is produced. So water vapor and carbon dioxide gas are produced here. Both of them are coming through this medium, and this medium is made of something that can absorb the water. So water being absorbed from here. If water is absorbed, only carbon dioxide is left. So this carbon dioxide goes there and then go through this bed or this thing, so that carbon dioxide is absorbed already from here. There is no carbon dioxide. And then there will be oxygen as well, produced. So the oxygen is coming, only the oxygen is coming out. Unused oxygen is coming out from that. And analyzing this oxygen, we can find how much of the ethanol, or what is the empirical formula and then molecular formula of the ethanol here. The question is saying, the problem is giving us that we combusted that 11.5 gram of ethanol. In this experiment, 11.5 gram of ethanol was combusted. And the collected gas, we have to know that how much of this water and then carbon dioxide was produced. In another way, actually, we can find, if we just find how much oxygen was produced, right? How much oxygen was produced. From there, we also can find how much of this ethanol was combusted. That is another way of finding out. This is doing the analysis. But for this problem, it is much easier. It says that for this experiment, we have collected 22 gram of carbon dioxide and 13.5 gram of water. So what will be the molecular formula or empirical formula for ethanol? Suppose that we do not know what is ethanol, what is the molecular formula or empirical formula of ethanol. That means how many carbon or hydrogen or oxygen are there, we do not know. So that is, we have to find out. Now, if we do the investigation thing, like if we go step by step, or logically, we see that carbon dioxide was produced, right? And water was produced, and oxygen gas was also produced. This G means not gas, this means gram. Okay. So this carbon dioxide, how much of carbon dioxide was produced, right? 22 gram of carbon dioxide was produced from here. So if 22 gram of carbon dioxide, then how many moles of carbon dioxide was used? Okay, or produced, sorry, not used, produced, moles. Because in chemical calculation, another thing, just to tell you or to remind you that in chemical calculation, chemical studies or consideration, the grams or liters or what do you call it? These things are not important. I mean, not that important. Only the number of moles are important in chemical equations. Okay, in chemical equation, number of moles are only important. We look into the number of moles. It doesn't matter how many grams or how many tons or how many liters you are using of that compound. So number of moles, most of the time, all the time, actually, we should convert to number of moles of that compound or chemical from gram or liter or whatever. And then we can return it back, convert it back to the gram or other units, but number of moles is very important. So gram of carbon dioxide, we have to find the number of moles of carbon dioxide, and then from that number of moles of carbon dioxide, we will find how many moles of carbon is there. From there, we can find the number of grams, all right? So here for this carbon dioxide, 22 gram of carbon dioxide, if we do the unit factor level calculation, right, that 22 gram of carbon dioxide, right? How do we find the number of moles? So in factor level calculation, we have to put the desired unit on top, the numerator, right? So number moles of carbon dioxide, mole of carbon dioxide, I already put the unit on top here. And we do not know how many moles, but from the periodic table and then from the calculation, we know in 1 mole of carbon dioxide, there will be 44 gram of carbon dioxide. 44 gram of carbon dioxide. How do we calculate this 44 gram of carbon dioxide? Actually, this is carbon is 12, right? And oxygen is 32, 16 times 2. Atomic, one atom of oxygen is 16. So 16 times 2 is 32. So this is 44 gram. The molecular weight of carbon dioxide is 44 gram. So this is here. And then this will be, if so the gram carbon dioxide will be cancelled out. 22 divided by 44, it will be 0.5 moles of carbon dioxide. 0.5 moles of carbon dioxide, right? Okay, another thing is, in 1 mole of carbon dioxide, how many moles of carbon there? Can anybody tell me? In 1 mole of carbon dioxide, how many moles of carbon? It is 1 mole of carbon, isn't it? Because here it is 1, but 2 moles of oxygen will be there, right? Atom. 1 mole of carbon atom, but 2 moles of oxygen atom. So in 0.5 moles of carbon dioxide, we will have 0.5 moles of carbon as well, right? So this is how we can find it. And now I delete. So this is how we found the calculation. From that calculation, we found it. And this is, at the end, we found that 0.5 moles of carbon, and that means 0.5 moles of carbon dioxide, which is 0.5 moles of carbon, and 5 moles of carbon in that unit factor level calculation. Again, go back to this 6 gram of carbon. In 5.5 moles of carbon means 6 gram of carbon. So now we go the same way for water. How much water is there, and how many moles of water is there, and how many moles of hydrogen will be there. You may say that why you are considering carbon and hydrogen but not oxygen. We will be considering the oxygen as well, but it is a little bit later, okay? Just, you can do it first or you can do it later. Because in unused oxygen, there is no amount given. There is no amount given. So we do not know how much oxygen was produced. All right, how much oxygen we do not know. So that's why I'm coming later on for that oxygen. So hydrogen or water, how many gram of water was used, and then from there we can find how many moles of water is used and how many moles of hydrogen in water, right? In one mole of water, there are 2 moles of hydrogen, right? So from here, if we know the number of moles of water, we will find the number of moles of hydrogen in the water, and then from there we'll find the gram of water, and it is showing that 1.5 moles of hydrogen is present. Actually 0.75 moles of water is there. So in 0.75 mole there will be 1.5 moles of hydrogen, and since hydrogen atomic weight is 1.0008, right? So it is almost 1. We can consider, not all the time, but for our convenience, we can consider is just 1. So 1.5 moles divided by 1 is 1.5 gram hydrogen is there. Now, the unused oxygen. How do you find the unused oxygen? Because depending on the conservation of mass, there is a theory conservation of mass. We will talk later on that the total mass will not be changed. Whatever is going in, the same mass will, the mass will not change. It will be same thing. So depending on that, unused oxygen will be the total minus these two, right? Total minus these two, then we will find the unused oxygen. So 4 gram of oxygen we find, right? So 4 gram of oxygen means 0.25 moles of oxygen in that ethanol. All right. So what will be the empirical formula of ethanol? We know all the carbon and hydrogen and oxygen in it, but what will be the empirical formula of ethanol? So for empirical formula, we do not have to do all those steps, because most of the time it will be given that how many gram of hydrogen and oxygen and so on are given here. So here, as it is given that how many grams in 11.5 gram of ethanol, there are 6 gram of carbon, 1.5 gram of hydrogen, and 4 gram of oxygen is there. So we have to convert it back to the number of moles. How many moles of carbon? Because in a molecular formula or in a compound, the atoms are arranged by the mole fraction. Okay, it is, it is represented that they are formed in a mole fraction. They are arranged in a mole fraction, and that is why we should remember, or we should try to find out the number of moles that they have in that compound. And if we convert this to number of moles again, we see that 6 gram of carbon, and carbon number of moles is 12 gram per mole, so it's 0.5 moles of carbon, and so goes for same thing for hydrogen, 1.5 moles, 0.25 moles of oxygen, all these things. So now we have seen the number of moles of each of the element, number of moles of each of the elements. All right, we have to find the simplest ratio of the moles. Simplest ratio of the moles means we will divide it by the smallest number of mole among them. If there were another 2 atoms, let's say that nitrogen, and nitrogen was 0.5, 0.5 is here already, right? 0.3, and then chlorine was also here, which was 0.15, right? Number of moles. Let's say, for example, I'm saying the nitrogen was here, it is 3.3 moles. Chlorine was 0.15 mole was present here. So each mole element of them, we should have to divide by the smallest number among them. 0.5, 1.5. Of course, 0.5 is less than 1.5, right? This is 1.5. 1.5. So 0.5 is less than 1 point, but 0.25 is even smaller than 0.5. In this case, where we had 0.3 moles of nitrogen, 0.15 moles of chlorine, we would have 0.15 moles of chlorine, which is even smaller, so that we would divide all of those by 0.15. What we have done it here to find the ratio, smallest, uh, each of them, how many part of them is attached in relation to the smallest number. So this is how we should find it, and then this is the empirical formula. We found that the 2 carbon here, because this is carbon, right? This is for carbon, this is for hydrogen, and this is for oxygen. So 2 carbons are here, hydrogen 6 and oxygen is 1 here. Now you may ask that what if we had 5 point, not 6 but 5.9? What if we had 5.9, right? So 5.95, 5 or 6.012, 025 or something like that, we should have round it up or down to the simplest number. But if we had 2 point, let's say here 2.48, even after dividing it with the simplest number, the smallest number, we would get 2.48. So what should we do? So in this case, we will multiply it with a integer, with a whole number. It can be 2, it can be 3, it can be 4, it can be 5, till we get a closest to an integer. So if we, for this case, if we multiply by 2, we would get around 5, right? And this multiplication by 2 should follow to everyone. This 6 would be multiplied by 2, this one would be multiplied by 2 as well. If it were 2.33, 2.32, let's say, then we should have multiplied by 3, so that, is it 3? Yeah, so that it will be around 7, rounded up to 7, and this 6 will be multiplied by 3 as well, and 1 will be multiplied by 3 as well. So in that case, C will be 7, hydrogen will be 18, and oxygen will be 3. So this is how we should find out the empirical formula. Okay, so since we have found the empirical formula, how do we find the molecular formula? Okay, we are coming to the molecular formula later on, but for this case, this is an example was given. Usually, I mean, when we do in the class, this example the student would have to do on there, but since we already have published it, and then I hope that you have had a look, it's pointless to go and ask you to do it now. Okay, so for this ascorbic acid, what is a vitamin C that we see in the in lemon juice or in many fruits. So this vitamin C, it is very important for us human body, because we cannot produce it. We have to have it from foods or outer sources. So it is composed of 40.92% of carbon, this many percent of hydrogen, and percent of oxygen. So when we say it's percentage, and all together, if we sum it up, it will be 100%, right? It will be 100% or very close to 100%, 99.9 something percent, maybe something. So we just consider everything in this percent to a gram. So we can consider that we have 40.92 gram of carbon. 4.5 8% or 4.58 gram of hydrogen and 54.5 gram of oxygen are there. So since we already know the number of grams of all those, we just start to find out the number of moles of each of the compound atoms, and we find the number of moles here and divided by the smallest ratio that we have. So here in this case 3.406 is the smallest one. Is we divide by it, we find the number, what do you call it, almost integer, that is 1, almost 1, we can consider is 1. And here for this case we find it is a fraction 1.33. So what we do is we have to multiply by 3 until it becomes an integer or as a not fraction anymore. And the formula of ascorbic acid is this. So now we know that this is the empirical formula of acid, and then this is for ethanol. How do you find the molecular formula? That is what we want to know, that molecular, what is the molecular formula? How does it look like? How many carbons and hydrogens are where, right? So the molecular formula, we have to know the molar mass of that compound. If we want to know the molecular formula, we have to know the molar mass. And if we divide the molar mass by the empirical formula mass, that means how many carbons and how many hydrogens and how many oxygens we have, we divide by that number, we will find the ratio, that how many we have to divide or multiply or what. So the molecular formula of the ascorbic acid will be C6H8O6 and O6. So this is actually it should be the molecular formula, so that we know that in one molecule of ascorbic acid there are 6 carbon, 8 hydrogen, 6 oxygens are there, atoms in one molecule of ascorbic acid. So this is how we should be finding that molecular formula for it. So in this time, I will take a 5 minutes break. You can go and have some drink as well if you want. I'll see you after 5 minutes. I'll start after 5 minutes. Hello, I'm back here. I hope that you are there also. You come back. And I can see there are some are not attending the class. So who is there as guest? Can you please tell so that I can keep the record, attendance record? One zero one two two 5503. Who are you? What is your name, please? Alvin. Okay. Alvin is here. All right. Shafab, you are not here, right? Shafab is not here. Muhammad Ali is not here. I don't know why it asks me to use that instead. I'm not sure what you're talking about. Okay, Shafab not here. Muhammad Ali is not here. Who else is not here? Rachel, are you here? Rachel. Okay, thank you. And Michelle, are you here? Okay, you're here. Zixing Liao. Zixing Liao, are you here? Oh, you are as a guest as well? 101225503. Okay. Oh, this is you, not okay. Jolene, are you here, Jolene? Jolene. Jolene is not here. Okay, I found out. All right. So let's go to the lecture slide again. Do you have any question? Anyone else? Anyone? Does anyone has any question? I'm going to the full screen mode. I will not see you if you type. So please stop. Okay. All right. Now I'm going to the full screen. All right. Formation of charged ions. Now the ions are formed. Can anybody tell me where, why, and how the ions are formed? Or how, not why, but how? how the ions are formed. Counting once, counting twice. Nobody? When these atoms shades an electron or take some electron, they will be imbalanced in charge, because the charge is balanced due to its proton, and proton is positively charged, electron is negatively charged. So based on that, we see that there will be neutral. The same number of proton and electrons are there, so it is neutral. And if there is any imbalanced in that charge, like more proton, less neutron, or more neutron, less proton, that will be a charged particle. But they cannot just simply take the proton and throw the proton. That is because we already told, right, that is their identity. So what they can do is they can take or throw or release the electrons, and thus they will be positively or negatively charged. And metals, they always, as I said, that on 18, group 18, right? So they are the noble gas. They are the noble gas here, and everyone wants to attain that electronic configuration of a noble gas. So what happens is, until here, here, in fact, they will try to release the electron and try to be closest to that noble gas structure. So if they release the electron, they will be, that is why metals will always be positively charged. Metal always tend to form positive charge, positive ions, because they lose the outermost electrons, shell electrons. But non-metals, they will try to take an electron and then they will form a negatively charged electron, non-metals. Okay. And that is called the two things, that ionization energy and electron affinity. These two things, these two criteria comes in this case. So ionization energy is to remove an electron from a gaseous atom or ion. Okay, so it is always positive, because you are trying to remove an electron from an atom. The atom is quite good, they're stable, they are enjoying there or whatever, but you are taking the electron away from it. So what you have to always give some energy to it. You have to provide some energy to it, so that only it will be able, or it will be tricked to release that electron. And that is why it is shown as a positive charge. Electron affinity, this is another specification for elements, that the energy, when the energy is released, when we add an electron to an atom, right? So that electron will be, some energy will be released if we add an electron to an atom, like this nitrogen and oxygen or fluorine. They are very much electronegative. So if we add an electron to them, they will, from that excited state, they will go to that very much, much stable state, and that in that process they will release some energy. So it is called the electron affinity, how much they want to take that electron and release the and electron affinity also, it is supposed to be negative, but it is also shown in positive, because in negative form, negative sign sometimes confused with the instability, but actually electron affinity, the elements, they want to be stable. That is why it is shown in the positive way. And for the maximum here on the periodic table is electron affinity for fluorine, which is very high. Fluorine is very electronegative, so it always try to take electron, and it is very stable when it is very easy for it to take electron for you. Okay, the electronic configuration in sp-d rotation and lithium ion and lithium ion. So lithium, can anybody tell me that whether it will form a positive charge or a negative charge? Anybody? I cannot see your text box, so if you want to say, you have to say. Speak. Okay, lithium is an it is staying on the periodic table. It is on the left side, that is the extreme left column, that is the first group, and just beneath the hydrogen. So it is designated as a metal. Okay, lithium is a metal, and it is more precisely is called alkali metals. Okay, so since it is metal, it will be electrons will be released from here, and they will form a positively charged. So in this case, we can see that there are 3 electrons. This already is given 3. This is not the electron, is the number of protons. So since there are 3 protons, there are supposed to be 3 electrons, and then proton is positively charged, electron is negative. So in that way, it is no charge. Here is 0 charge, right? There is no charge here, and that is why it is not shown anything, or 0 is not needed to be shown. So it is 0 charge, is stable, is not charged yet, and this is the electronic configuration. But now if it wants to release 1 electron, right, if it wants to release 1 electron, so what will happen? There will be no 2s anymore. 2s is gone. If 2s is gone, then only 1s2 is there. The electronic configuration for lithium, only 1s2 is there. And if you look at the periodic table, this 1s2 is the electronic configuration for helium. Okay, 1s2 is electronic configuration for helium, and that is why lithium wants to be like helium, because helium is a noble gas, and it is very stable. It does not do any reaction, or it does not undergo any reaction. You cannot force it. It's not easy. It's very hard to force it to go for any reaction, and they are very stable in the environment. Wherever they are staying alone, and they are easy, relaxed in that way. So this is a very stable configuration, and that is why lithium always want to attain this electronic configuration. So to attain this, it has to release this 2s, that is 1 electron at the outer shell. It has to release this one, and it releases this one, it becomes lithium positive. So it becomes lithium positive. Still it is 3. There are 3 protons here still, but there are 2 electrons. So there is a positively charged, is shown in this way. So there is a positively charged 1. So lithium, now it attained this electronic configuration of helium. Okay. So, okay, another thing is says that fluorine atom and fluoride ion. Fluorine atom is 9. There is a 9 proton in fluorine, and it is stable here. It has 9 proton and 9 electrons, so it's supposed to be stable in this case. But since fluorine is very near to the neon, right? Because neon has 10 electrons in it, and by having 10 electrons, neon is very stable. It's just after helium, there is neon. So it's also noble gas. So what fluorine will also try to attain that neon structure. And here we go is for the electronic configuration for fluorine. So in 1s there are 2 electrons, there are 2s, there are 2. We have total 9 of electrons, so the balance is 5. So 2p is there is 5 electrons here. 5 plus 2 plus 2, 4, 9. So this is the electronic configuration for fluorine. But fluoride, that means if it has to take the neon structure, right? Neon is 1s2, 2s2, 2p6, right? Two p6. Okay, so this is neon. And to get 2p6, here the 2p5, so we have, if fluorine wants to get another one, so it will be 2p6 as well, but here there will be -1 charge. Okay, it will be shown as -1 charge. That is the fluoride ion. In SPD notation as arsenic, and you know that arsenic is very carcinogenic. Oh, before that, I forgot to mention that lithium is, we all know that lithium nowadays, it is every one of us are carrying, because it is in our phone battery, smartwatch batteries, and so many lithium is used, lithium ion battery. This is the one thing, that lithium is very easy to release the electrons, and that is why. But lithium, another thing is, lithium is a very small amount of lithium is found on Earth. So this is very expensive in that sense, and it's not easy. All right, so arsenic is, there is another, since we are here, there is another research, there are many other research to use other alkali metals, right? And because in group 1, just after lithium, we have sodium, we have potassium, we have rubidium, cesium, francium, all those alkali metals elements are there. So scientists was thinking that if lithium can be used, why not others? Why not sodium or potassium? Well, we can discuss it later on, but there are some research going on. Actually, there are quite successful research about with the hello, can you hear me? Anyone? Hello, can you hear me? Hello, does anybody hear me? Please, can you confirm?
Yes, yes, we can
Okay,
hear you.
thank you. Okay, so it seems like my network was dropped anyway. So now, what I was talking about. Okay, so helium. Okay, lithium. Yeah. So now we are going to the arsenic one. Arsenic is carcinogenic, and it is also a very small amount we can find in the earth, but it is highly carcinogenic. Some of the our water is, some of the water, underground water even, are contaminated with arsenic. The good thing is on the surface water there is very less to no arsenic found in the stream, but underground water, yes, most of the deep tube oil we get arsenic. So this is important to know, and it works as a slow poisoning, sometimes works some like slow poisoning thing. Okay, so write the electronic configuration of SPD notation here, and then later we can we see that arsenic here is producing 3 negative charge or ions. All right, so it means that it has taken 3 more electron. It has taken 3 more electrons for it, and thus it formed the arsenic 3 negatively charged. And we see that here it was 4p3, now it becomes 4p6, right? Another one, arsenic can also shed these 5 electrons at the end, so that it becomes arsenic 5, right? So it can shed all those 5 electrons, and then it becomes positive 5 electrons, and the configuration is as well. It goes this way. Okay, so now another thing, just to remind you that it is written in this way just to show that how the configuration will go. But it is, since arsenic is a metal and it will release the electron and become positive, then take the electron and become negative. So it was put here just to make sure, I mean, to show you that if even it's negative or positive, how do we write the electronic configuration? All right. Okay, so now we move on to the chemical formula. We already have seen that ions, when the ions are formed, what ion and what metal we can expect from where on the periodic table, right? So the chemical formulas we should be able to write, or when it is given the chemical formula, we should be able to know the name of it, because it's important. If we do not know the name of the chemical compounds, we will not be able to identify it or find out the property of it. So we have to find the name or to express it. Okay, so it says that cesium, first of all, we will go some example of it, the name of the compound, okay, formula, and why it is naming, why are we naming in this such form. We will talk later on the criteria for naming of chemical compounds. Number A, it says the cesium sulfide. Okay, so what to note here is cesium. This is a metal and it is a D block element we can find. Sulfide. Sulfide, from here we see that it is it coming from sulfur, and it is also a P block element. So it is, but interesting thing is ide is added, IDE. Sulfur, from sulfur it is not sulfur anymore but sulfide. This another one is mercury, right? After mercury, there is one Roman number is put in between them, and then from nitrite, it is ide, it is ite is here, and nitrite, we know it is coming from nitrate. Okay, this nitrate. Calcium, we see, we know that it is a metal, alkali earth metal, and S block, right? Mercury is D block as well. It is S block. And phosphate, ATE is added, and phosphate is coming from phosphorus, right? So this is another thing that these are the differences we are noting here. One is ide, one is ite, another is 8, okay, another is the Roman number in between them, and then calcium chlorate as well. The 8 is same thing here. Is that it? So this is coming from chloride. And ammonium, calcium, mercury, cesium, these all are, I mean, cesium, mercury, and calcium, these are the metals, and their names are almost unchanged. So these are the few things that we can note from the names of a compound, of compounds. And if we want to write the chemical formula of the compound, we'll see the cesium sulfide. And cesium, if we look at the periodic table, it will be, we'll see that it is producing one positively charged ion, and sulfur, it produces two positively charged ions. So if it takes 2 electrons, then it will become very stable. If it releases 1 electron, it will become very stable. So cesium will release 1 electron and produce cesium plus 1 ion. And from the periodic table, if we look, is it there? Okay, so it's not shown on the ions, but okay, here, cesium, right? So cesium is alkali earth, alkali metal, and then it is S block, so it can produce only one charge state. That means one positive charged state, and it is on the group 1, so it can produce only one. Okay, the group 2 will produce 2 charge state, but this D block, the metals on the D block, they have multiple different charge. The metals has multiple different charges. They can different charge they can form. Okay, so now we move to the cesium again. The cesium sulfide. Cesium is one positive charge. Sulfur producing 2 positively negatively charged. So how do these form a compound? In this case, if they come together, one positive charge will neutralize one negatively charged sulfur atom. But what happens to the another negatively charged, right? This one positive charge is neutralized, 2 negative charge is neutralized by 1 positive charge, and then there is another one left. So if we add 2 cesium, then this is neutral, no more anymore, because cesium, sulfur, and then cesium again. So sulfur is attached to 2 cesium, and then its 2 positive charge is neutralized by each negatively charged. So in this way, we see that they are forming the compounds. Mercury nitrite. Again, this mercury, there are 2 positively charged, and nitrite, it is 1 negatively charged. So there will be 2 nitrite to neutralize the 2 positively charged mercury. All right, so that is why this 2 is shown here. This 2 is shown as well after this. But when we are showing these 2, when we are showing these 2, right? These 2 means there are 2 NO2. There are 2 NO2, each of them carrying 1 negative charge. But these 2 means there are 2 oxygen only in 1 NON. There are 2 oxygen in 1 N, right? So these 2 and these 2 are different, and that is why it is in the parenthesis or in the bracket. Okay, calcium phosphate. Calcium, and there are 3 phosphate, 2 calcium and then 3 phosphate are there. So in this case, what should we do is we should multiply this calcium. Okay, sorry. Yeah. Sorry. So there are three phosphate here, and then two calcium positive here, and three negative here. So what we'll do is we will multiply this 2 here, and then we'll multiply this 3 here to produce the calcium phosphate compound. So calcium, there are three calcium required, and there will be 2 phosphate ion required to produce that the compound. And same goes for ammonium chlorate, and ammonium is 1, chloride is 1, so they just need 1 and 1, so it will be ammonium chlorate. Now we see that how these charged are placed and how these charged are the charged compounds are what do you call it, ratios are put between them to produce the chemical formula. Then the nomenclature, actually why do we call it cesium sulfide, ide, right, is ite, 8. So what are the things, what are the rule that we should call them ide or 8? There are nomenclature for this inorganic compounds. We will be studying the inorganic compound for first 6-7 weeks, so that the nomenclature for inorganic compound is different than that of organic compounds. Organic compounds nomenclature we'll see later on, but for this now, the binary compound, there are certain rules, but remember that you cannot put everything 100% into this rule, but we can have a very good idea of what will be the name of that compound if we follow this flow chart. Okay, so if we see if there is a binary compound means there are different type of ions are added. All right, different types of ions are added into that compound, so it is calling the binary compound. So if it is a binary compound, and if it is yes, then whether there is a metal present in it. If there is no metal present, then we will be using prefixes, right? So you will use prefixes. What are those prefixes and why it is in 3? What should we do in 1 and 2? We will describe it in a bit. But if there is a metal present and it's a binary, if there is no metal present and it is a binary, then it will be type 3. Just remember that no metal but binary, it is type 3, just like ammonium chlorate, right? Ammonium chlorate there is no metal here and it is a binary compound. So it is a type 3, we should be using the prefixes. If it is metal, if there are metal inside that compound, either the binary one, and if we see that that metal has more than one cation or not, because just now we have seen that the metals in the D block element, they can have more different oxidation state. That means they can form different type of ions. Some of them can form 2 and 3 and 4, some of them 2 and 5, just like that. So if they can form more than one cation, then it will be type 2. Okay, we have to determine the charge of the cation, and then we put the charge in between them. It is shown in the number B. So mercury 1, that means it can produce one type of charge. Okay, and then if it does not produce any more than one cation, it only has one type of cation present in it, then it will fall under the type 1 compound, and we will use the element to name the compound. So type 1, the first one, that it does not have any, it has a metal, but the metal does not have more than one oxidation state. So we will find the ionic compound, metal and non, it is the ionic compound, and then metal and non-metal are present in that compound, in that ion. And metal from the group of elements with one oxidation state only, that means it does not form more than one charges. Either it will be +1 only, or it will be +2, or +3 only. It will not have +1 or +2, +1 or +3 like that. It will not. Okay. And then for that nomenclature of that compound, we should always maintain the name of metal, whatever metal it is. Okay. And then we will add the IDE to the end of the name of non-metal. Because it is an ionic compound, that means there is a metal and there is a non-metal, both in that ionic compound, right? So if there is metal, all right, and we will always keep the name of the metal. The metal name is unchanged. There is no changes in the metal, or there is no addition of the name in the metal name. We will always keep the metal name, and then we will use IDE to the end of the name of the non-metal. Like example is BaCl2. So BaCl, this is only one charge it can produce. Okay, it can only produce barium is in alkali earth metal, right? Yes, barium is alkali earth metal, and it always produces 2 positive charge. All right, it always produces 2 positive charge, so that it does not change the oxidation state, or there is no variation in oxidation state. So now there's non-metal is chlorine is added there. So barium is unchanged, the name, but at the end of chlorine, IDE is added. Okay. Another example is potassium oxide, because potassium is alkali metal, is the group 1. It is group 1 element, is group 2 element, right? Metal. So it does not change. This potassium does not change. It's always +1. Potassium, sodium, potassium, magnesium, not magnesium, sorry, cesium, lithium, they are always 1, so that +1, so that they will not, I mean, hello. Hello.
Yes.
Okay, thank you. Precious. Okay, I don't know. This is I'm in the office, and then office the network is not very stable. Looks okay. So okay, so this is what I was talking, that for ionic compounds, when there is 2 metal and non-metal there, IDE will be added. The name of the metal will always be the same. It will not be changed. Okay. And then magnesium hydroxide. Magnesium has only one oxidation state. Has a zinc phosphide, right? Although zinc is not very suitable to put here, but just to show. All right. So now we see that the IDE nomenclature of some common monoatomic ions according to their position on the atomic table is group 4A carbide from carbon, silicide from silicon, nitride from nitrogen, phosphide. So you see that IDE all are added to the non-metals, all right? These non-metals, so IDE are added at the end of their name. Okay. Just to remember that carbide, for a carbide, the C2 negative charge is also used for carbide. Type 2 compounds with transition metal, when the metals are used, right, in the transition metal, we call that is the D block element, and they all of them show that they have multiple oxygen state. Uh, Multiple oxidation state. Uh, for example, go to that table again. Here we see that chromium has 2 positive charge and 3 positive charge as well. Manganese has 2, 3. Iron has 2. So everyone has different oxidation state. So they vary, and some of them has even 5, 6 oxidation state. So they vary the oxidation state very much, and that is why when you name it, you have to indicate at what oxidation state it is at that time, or in that compound, what oxidation state they are staying. So that is why we have to indicate the charge of the metal in Roman numerical. Like iron chloride, iron can have 2 and 3 both, right? Iron can have 2 and 3 both. So that iron chloride is here, and we show that it is a 2 oxidation state for this iron. And of course the chlorine is an non-metal, so the ide will be added as well at the end of their name, because chlorine is from the non-metal. So ide is added, but iron, we have to show that it is a 2 oxidation state. How do you know? Because from here we can see that chlorine, each of them carry 1 negative charge. There are 2 chlorine added, so that it should be, iron should be 2 positively charged. Only then it will be neutralized by added 2 chlorine negatively charged. So that is why iron 2 chloride is added, written in that way. Iron 3, since there are 3 chloride is added here, and each of them are carrying 1 negative charge, so that iron will have 3 positively charged for sure, so that after being added 3 chlorine, it will be negatively neutral. So that is why it is shown in this way, the 3 negative charge, iron 3. And what is the purpose of showing these 2 and 3? Because they have totally different characteristic or chemical properties. Iron 2 to iron 3 chloride, they have different chemical properties, and that is why it is very important to show their oxidation state, or write in that way. Cobalt nitrate. So this nitrate, ide, all those things stays for this type 2 name, okay, but only the new thing is added is their oxidation state, 2 or 3 or whatever the oxidation state should be added there. Chromium sulfide. Chromium has 3 oxidation state, and then that is why 3 is given. Lead sulfate, copper iodide. So all this thing is added in that way. Okay. So type 3, the metal and non-metal are added in this way, that non-metal or metalloids plus non-metal. So if there is both of them, so far we have seen metal plus non-metal, but if non-metal and metal are added, just like here, remember that ammonium chlorate, right? Here both are non-metal, ammonium and chloride. Chlorate is coming from chloride. So is added, and both of them are non-metal. So where is it? Okay, will be added, and since both of them are non-metal or metalloids, so which one should come first? Which one should we put first? Which one name should we take first? The thing is, which one is the, where is the periodic table? Yeah. Which one on the element is extremely left or relatively left to the other one, or the bottom of the periodic table, either on the bottom or left. So can I draw? I'll finish soon. Okay, so here, yeah. So here is going down and then left. Whichever element on the left side, relative left side and relatively bottom of the periodic table will come first for this. For 3 metal. So closest to the bottom or in the left will be put first on the for the naming, and the other element name should end with IDE, IDE. If more than one compound can be formed from the same element, use the prefixes to indicate the number of each kind of atoms are there. So again, we will be using the prefixes of how many types of elements are there in that. And prefixes is the mono, di, tri, penta, hexa, all those things. So here, hydrogen iodide, both of them non-metal, right? Hydrogen is a gas, iodine is a gas as well. So what we see is, what we do is, why don't we call iodine hydrogen, iodide or iodine hydrodide, or whatever. We do not call it that way. To stop that, that is why the rule came out that hydrogen is the left side, right? Hydrogen is on the periodic table. On the periodic table, hydrogen is here, and iodine is here, somewhere here, right? Iodine is here, hydrogen is on the extremely, relatively much left on the periodic table than iodine, so hydrogen comes here. Same goes for nitrogen and fluorine. Fluorine should be on here, and nitrogen is somewhere here. So nitrogen is left to fluorine, so that is why nitrogen fluorine is coming. But since there are 3 fluorine, we do not put 3 fluorine 3, right? If we put fluorine 3, that would be totally different thing and it will be wrong. So 3 fluorine atoms are added, so trifluoride. The prefixes has to be used, so trifluoride are there. So here it is dinitrogen tetrachloride. Dinitrogen because there are 2, and tetra means 4, so tetrachloride, and so on. It will be said in this way. All right, I think I'll stop here today, and tomorrow we'll finish this up for the acid and how to name the acid and what else. So far, do you have any question? Does anybody have any question here today? Now? Okay, Precious. No question. What about others? Okay, so seems that it is very good. You understand it very good, yeah? Muhammad Tahar. What you say no, that means you understand it not good or you don't have any question. Okay, so the thing is, I assume that you don't have any question, and that is good that you understand. If you have any question, anything, I repeat, anything, any question, it not necessarily has to be from this topic today, lecture, anything, you can ask me anytime, okay? You can email me or you can directly ask me the question. I like to have some question and talk on it better than I'm talking alone myself. Can somebody volunteer to ask any question? Okay. Now, one thing that I will update, sir, we have 3 lecture session once a week. No. We have 2 lecture session. One a week. We have 2 lecture session today and tomorrow, Wednesday and Thursday. Please refer to your timetable. But yesterday was the tutorial from 4 to 6, right? But I saw the tutorial from first lecture was not much. We did not need 2 hours to do that. So I took that opportunity to do some lecture session yesterday so that it will be easier for us to finish by this week. That's why I do 1 hour or half an hour lecture yesterday. So we have 2-hour tutorial every week, 3-hour lecture, 2 hours on Wednesday, 1 hour on Thursday, and every alternative week we have 1 lab session, 3 hour, okay, Monday, 2 to 5 Malaysia time, of course. Everything is Malaysia time because I am in Malaysia now. Amanda, sir, lab 1 will due before lab 2. Yep. Lab 1 will be due on before lab 2. And then, once again, how many of us are here? 20 of us are here. So once again, I'll tell you that you will see if you, after I send you the, what do you call it, the data for lab 1, there will be a link available to submit your lab report, all right? So in that link, you will, if you click, you will see that when is the due date. It will show you when is the due date. It will be before lab 2. All right. So Amanda, since you started this lab, so can I ask that, have you already talked with or discussed or say hi to your group member? Can you see your groups on the canvas? Is there anybody who cannot see? Muhammad Usman, yeah, I haven't put the recorded yet. I have put just uploaded to YouTube. I will share the link by now, by after this class, okay? Because it was late here, so I left. Okay, so Amanda, Anupaja, you can see your group members. You can see your groups here, right? So that is good. That is good that you can see. And another thing is, those who haven't submitted or sent me your assignment group, please send so that I will assign you to that group, so the assignment group. Another thing is, important thing, that you don't wait for others to ask you that, hey, let's do the lab, or how are you? You initiate, please. You initiate it. You send an email to your friends, okay? Don't wait for others to start the discussion. Okay, so that if somebody does not respond or somebody is not cooperating, please let me know. Okay, so I'll see you tomorrow at 1 p.m. Malaysia time. So take care. Goodbye.